In this video, we're going to be talking about optimization. So to do that, we need to basically describe for a second what optimization is. Optimization is when you're trying to sort of find a maximum or minimum of something. For example, you might be minimizing cost when you're trying to optimize your financial models, or maximizing revenue when you're trying to optimize financial models. And there are all sorts of, unlike some mathematics, which is sort of done for its own sake, optimization is something that's very broadly applicable in a lot of fields. So before we talk about optimization, let's just recall basically something called the extreme value theorem, which says that if you want to find maximum and minimum values for a continuous function on a closed interval, then you find the critical numbers, then you evaluate at the endpoints and at the critical numbers. The largest y value is the max, the smallest y value is the min. And as long as you have a continuous function on a closed interval, you're guaranteed to get an absolute maximum and an absolute minimum. Okay, so let's see what optimization looks like. Basically what we're going to be doing is using the extreme value theorem, but also adding the layer of these are usually word problems. So for example, this is kind of a classic one. A farmer wants to put a rectangular animal pen next to a river so that the river makes one side of the pen. If the farmer has 200 linear feet of fence, what dimensions will maximize the area of the pen? Okay, so to start, let's just rough sketch out what's happening here. So we're going to have some sort of rectangle. We don't know the exact dimensions. And then there's a sort of natural barrier on one side of the pen. Okay, so he's only going to have to build 3 sides of the pen. So we don't know what this is, right? But we do know that these are the same, and then this is potentially something different. Rectangular allows for the possibility that it's a square also. So in general, what you generally have in an optimization problem is you have a function that you're trying to maximize, and then you have what's called a constraint function. So what are we trying to optimize? We're trying to optimize the area, right? Specifically the area of the pen. That's the thing we wanted the maximum of. Maximize the area of the pen. So we're trying to optimize the area of the pen. And then what's our constraint? In this case, the constraint is the fact that we have 200 feet of fence. So we're trying to build the biggest area we can, but our constraining relationship is this. So what you're going to try and do is turn both of these into equations. Okay, so specifically, you might ask yourself, how is this 200 feet of fence going to come into play? And you might pause and ask yourself that question, so go ahead and pause. Okay, so if you're back, the constraint is that the 200 feet of fence represents the perimeter of the fence, and specifically it's the perimeter of this 3-sided pen. So we know that 2x plus y, that has to be less than or equal to 200. Now, but I'm going to go ahead and assume that it's actually equal to 200 because common sense tells us if you want the biggest area pen, you're going to need to use all the fence that you have. Okay, so I'm going to set that these are equal to 200, and then, so this is my constraint, and then the thing I'm trying to optimize is area of a rectangle, right? So the area is going to be x times y, right? Area of a rectangle. So then, in general, when you're taking derivatives, unless you want to use implicit differentiation, right, then you don't like to have more than one variable, okay? So what we're going to try and do is eliminate a variable. So specifically, we use the constraint to eliminate a variable. So we're going to use this to eliminate one of our variables. And in particular, you can see that this pretty easily gives us that y equals 200 minus 2x. So maybe we'll just do that, right? Move the 2x over. So after we remove our variable, then we get a is equal to x times, and instead of y, we'll do 200 minus 2x. And because I don't want to have to do product rule when I differentiate, I'm going to go ahead and just distribute this out. So 200x minus 2x squared. So now we're basically trying to optimize this function, right? Okay, so that's not too bad. This is what we were stated at the beginning in green. If you want to optimize a function, you want to find a maximum and a minimum, you take the critical numbers, you evaluate at the endpoints in the critical number, you take the largest and smallest y value. Well, so what is our variable? Like, what are our constraints for x here? So you might pause and ask yourself, like, what are the possibilities for x? And it turns out, so if you're back, x we know is going to be from 0 to 100. How do we know that? Because x we labeled as sort of there being 2 of them. So if we want to use all our fence on these x's, obviously that's not going to make a maximal pin. You're going to have 2 100-foot lengths laying right next to each other with no area. And similarly, if you have all 200 feet just laying in the river, that's not a good pin either. So it turns out we can sort of tell by common sense we're not going to be using these, but this is the interval in question. So now what we need to do is find the critical numbers. So you may remember a critical number is something that makes the first derivative 0 or undefined. So I'm going to take the first derivative and get a prime that's equal to 200 minus 4x. This is never undefined, so I'm going to take it and set it equal to 0. So 200 minus 4x equals 0, 200 equals 4x, or x is equal to 50. This is my critical number. And it's the only one, right? So then the question is, which has the largest y values? So the last step after you get your critical number and your endpoints is you take them and you plug them in to your original function. So in this case, 0, 100, and 50. When I plug in 0, I get 0. When I plug in 100, 200 times 100, or 2 times 100 squared, those are going to be the same thing, right? So that's also 0, because common sense tells us if one of the dimensions is 0, you're going to get 0 anyway. So then the question is, what does 50 give us, right? So 200 times 50 minus 2 times 50 squared. So 200 times 50, that is 10,000, I think, if I'm doing my math correctly here. And then 2 times 50 squared is, right, 50 squared is 2,500. So then 2 times that is 5,000. So 5,000 square feet is the maximum area pin I can get, but that wasn't actually the original question. The original question is, what dimensions of the pin will maximize the area? So coming back and looking at x equal to 50, and remember my picture looked like this, x, y, x, x, y, and we figured out that y was 200 minus 2x. So the dimensions of the pin will be x is equal to 50 and y is equal to 100, right? Those are the dimensions that will maximize the pin. Okay, so this should feel a lot like extreme value theorem problems, except that now you've also got some sort of like extra context where you have to come up with the equations yourself, right? You're sort of doing word problems. Okay, so the next one we're going to do is another really common one, which is maybe you want to optimize something else. So find the point on the line that's is or are, because there might be more than one, closest to some other point. So you've got this thing in space. Maybe we'll try and rough sketch this up. So 4x plus 2, right, has a slope of 4, y-intercept of 2, and we're trying to find the point on the line that's closest to 1, 2. Okay, so first of all, you might not see the language maximum, minimum, right? Those are the sort of key words that tell you optimization. So you have to sort of figure out what's the constraint and what are you trying to optimize. Okay, so in this case, and you might pause and ask yourself these questions. What's the constraint here and what are we trying to optimize? So if you're back, the constraint is that our point has to be on the line 4x plus 2. Right? This is where we're getting our point. So we're trying to find something that's closest to this. And if we could choose anything, we would just choose this one, right? Because that's obviously the closest. But the constraint is we're choosing something that's on this line. What we're trying to optimize is distance, right? So we don't see maximum or minimum, but we do see the language closest, which means minimum distance. So to do a problem like this, you have to know the distance formula. And in case you've forgotten it, the distance formula for standard, xy space is the distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared. And this is just derived using the Pythagorean theorem, if you want to sort of draw a picture of that. And the reason I'm including a distance one in this video is because there's a very standard trick that makes the math way, way, way easier. So first, we'll get to that in just a second. I'm going to put an asterisk by this because this is what we're optimizing, but this isn't the actual equation we're going to use. Okay, so this is the sort of foundation of our equation, though. So for us, this is going to turn into x minus 1 squared, because our variable x we're just going to leave alone. That's playing the role of this x, but then we know one of the x values in question here is 1, the one on this point. Right, and then y minus 2 squared, right? Because we're looking for a point xy that lives on this line. So I have one of these is unknown, one of these is unknown, but the other two I do know. And we can do a little bit better than this, actually, because we have to eliminate our variable. And again, we'll use our constraint to eliminate our variable. And in this time, our constraint is the fact that y is equal to 4x plus 2. Right, our original equation. We know that if our ordered pair lives on this line, then y is equal to 4x plus 2. So now we've eliminated our variable, and we can clean this up a little bit. So this is x squared minus 2x plus 1. These 2's cancel each other out, and 4x squared is 16x squared. So this is the square root of 17x squared minus 2x plus 1. Now, if we go ahead and take the critical numbers here, that's not going to be, that's not very straightforward, right? It's going to be something kind of nasty. This is chain rule, etc. So here's a trick. Maybe I'll put it in a new color pen, because this is sort of an aside that's more generally true. So this is a trick specifically for optimizing distance. If you want to optimize distance, instead optimize distance squared. And effectively what I'm saying here is I don't have to worry about the square root. And if you think about this for a little bit, you might believe that it's true, right? Because distance is strictly positive, okay? So if I take something that minimizes my distance, then I'm also going to be minimizing the square, right? Like take a bunch of distances, 1, 2, 3, and put them in order. And when you square these distances, they're still in order from biggest to smallest, or from smallest to biggest in this case. So if I'm trying to minimize these numbers, I can instead just find the smallest one of these and then go back to whatever the original distance was. Okay, so we're going to think about minimizing this list, which effectively means no square root. So instead of thinking about D, I'm going to optimize D squared, which is 17x squared minus 2x plus 1. And before we do this, remember we're going to find critical numbers, then test the critical numbers and the ends, but we never talked about what the interval was in this case. And in this case, we don't actually have a closed interval, right? I'm allowed to choose any x value I want, or any ordered pair that I want on this list. So when I see this function, right, that I'm trying to optimize, the interval that I'm working with is the whole real number line. So a maximum or minimum may not exist, and in fact a maximum doesn't, but as you might be able to tell from the graph, a minimum does. And in case you're thinking about the geometry, in general, if you want to find the closest point on a line, you get it by dropping the perpendicular, right? So we're looking for this point on the line. Okay, so now we need to find the critical numbers. So we take the derivative of this and get 34x minus 2. This is never undefined, so we take 34x minus 2, we set it equal to 0, 34x is equal to 2, x is equal to 2 over 34, or 1/17. So this is the x value, but it said to find the points on the line. So if I want the y value, right, I also need to just evaluate f of 1/17, right, which our original function was 4x plus 2. So in this case, 4 times 1/17 plus 2, or 4/17 plus 34/17, or 38/17. So it turns out the point on the line that minimizes distance is 1/17, 38/17. And every time you do an optimization problem that involves distance, you're going to use this trick. Don't do that square root. It makes the math unnecessarily hard. All I have to do is find an x value that makes the smallest one of these, and whichever one it is going to automatically make the smallest one for regular distance as well. Okay, so this is a quick overview for optimization.